Okay, so today we will cover the left out portion from sets and multisets of the EC and cycles and inversions also we will see. All right. And the plan as of now in my head is that since so far, if we see, I have missed 4 lectures, right? There were 2
Yeah.
lectures from one particular week which I had cancelled. And then just after that week, we missed 1 lecture, and 1 lecture we missed day before yesterday. So 4 definitely lectures I have with me which I can hold, and possibly, like as I have always said, and the reason why we keep lectures a little longer, we need to cover a lot of material. So my plan as of now is that so there are few sections of this particular chapter which don't really need too much explanation. So what I would do is that I would be recording these lectures. I would send you a WhatsApp message maybe an hour or two ago. Okay. And if you are available, you join. What is my major restriction is that I have licensed Zoom account only on Wednesdays and Fridays. So if I want to record the lectures and hold them for longer than 45 minutes, I have to either hold them on Wednesdays and Fridays, or I will have to record them on my system locally with none of you as participants, and then upload them on YouTube, and then we can hold a small sort of discussion session on Zoom, like
Okay.
because that would not need a recording, and that is like, even if it is interrupted in between, we can rejoin again, how we did, I think, initially once or twice. Okay.
Yes. Hmm.
But why I feel that the second option is more doable is because I plan to finish this particular chapter before the next Wednesday's class, which means it would happen over the weekend and Monday, Tuesday. Because there is too much to be done, too much. Next chapter is small relatively, but still, I don't want to take risk. It's better to be faster than slowing down, no? And I don't know, I might be traveling again in a week's time, so yeah. So that is the thing. Okay. So anyway, keeping those discussions aside, we should come back to the main business, which is sets and multisets, from where we'll pick up from where we left last time. All right. So all of you got the assignment? Saw the assignment?
Yes.
There was some glitch with the internet. I uploaded it on Saturday, and then when I cross-checked it, it was not there. So then I checked, and somehow it, like, I don't know. I never knew this was even possible. But very weird. So let me know if you need more time, because since I prepared it and uploaded that time, so for that I had kept 1 week's time, इसलिए वो 7 तक का UC time वहाँ पे. But if you think you need more time now, then maybe we'll see something. ठीक है.
Okay.
Next weekend we'll have our quiz, so I will not clash the assignment and the quiz at the same time. So even if I release an assignment, the submission time won't be near the quiz, it would be after the quiz. So that way you'll have some relaxing time. Fine.
Okay.
Okay. Yeah. So there are two quizzes, right? And there is one NSEM. So one quiz happens in November 15, then possibly for the second quiz, I need your suggestions. When do you think would be a suitable time? Because after that, there has to be an NSEM also.
NSEM is during the end week of December, right?
Right. So if you want to really distribute it out normally, or rather uniformly, September 22 is when we started our lectures. I'm sorry. So that way, if we see like November 15 is already late for the first quiz, it should have actually happened maybe October end or October mid, right? So that way, I'm asking, I'm asking if, like, to keep it at a safe distance from quiz 1 and NSEM, where do you think should quiz 2 be put?
First or second week of December.
So you guys are fine if this, I mean, as in the next quiz comes within 15 days?
But what about the syllabus for the quiz? Like whatever you teach in the 2 week session.
Your voice is very feeble, Aglan. Can you be like little louder?
Hello.
Huh.
I mean, what will be the syllabus for the second quiz? Whatever you teach in between, like, or
Yeah, most probably. My
okay,
main funda always remains to be that it does not make much sense to check your understanding on the topics again and again. So I would mostly try to, keep them disjoint.
okay. So you will also need time in between the quizzes.
Correct. So
Yes.
enough teaching has to go. So one way out for this is that, since I mean, I told you, I think in the last time lecture also, that I have not prepared quiz 1 yet. So that is why I could not tell you the syllabus. So one thing is, for the quiz 1, if we do not keep the syllabus to be everything till that day, then we can keep up till some point for the quiz 1, which is much earlier than the date of the quiz 1. And then from that particular point till what you covered till quiz 2 becomes the syllabus for quiz 2. NSEM anyways is like full course, whatever we would have studied.
Yes, that is fine.
Yes, ma'am. This is fine.
That's fine.
Have you finalized the date for quiz 1? I mean, next week. Which day?
So like, see, November 15 happens to be a weekend, right? Or not? Okay, it's a
It's a
Monday.
Monday.
Yeah, so either 13th or 14th, something like that. Whatever suits you people better.
Yes, I actually have a quiz on 12th, and after that, 13 and 14 is fine. I mean, both weekend, I'm available on both the days.
Okay, but you should not later tell me that, ma'am, I had a quiz on 12th, so I didn't get time to
No,
study for a
no,
quiz on 13th.
no, that's fine.
I prefer 13th.
You prefer 13th, Saham?
Sorry, 14th. 14th.
14th, okay.
Yes.
So 14th on timings?
Any time is fine.
Any time is fine. So if we keep it early morning, will that work?
Around what time?
So let's say 5:30, 9:30, 10 a.m.
Yes, ma'am.
So can we fix it? Others?
Yeah.
Yeah.
Yes, fine for me.
Okay, so 14th, 10 a.m. IST. Right?
Yes, ma'am.
Okay. So, which date?
And the syllabus?
Syllabus would be everything covered up till last lecture.
Okay.
Okay. So anything which is going to be taught today and onwards is not part of the syllabus for quiz 1.
Okay, ma'am.
Sunday, November. Oh, great. November 14 is Children's Day also.
We are not
And-
children.
Oh, well, you are. 10 a.m. IST is a quiz. So, as I've told already, I do not plan to take any lengthy quiz. It would more be of the like cut type of a quiz.
This is written, right? Or how are you
That
planning?
I'm yet to figure out. I want to take it through Moodle, but I don't know how that happens. So I have to ask my colleagues and see.
But in Moodle, I think, I mean, if the questions are lengthy, you should assign it like an assignment. Or if you just put up the question, we can only choose some options. I don't think we can type much in.
Yeah, that's what. So I have to really figure out, I mean, how quizzes are conducted using Moodle. Many of my colleagues do it. Many of the professors at CMI do it. So I have to ask them like how, up to what extent is this even feasible? Because at the same time, like I do not want you to worry about typing or making auto correct mistakes. You'll already have less time in hand, so that time would should be used for mathematical thinking and not doing other stuff. I'm already assuming none of you who would try to take undue advantage of the fact that we are not in a classroom, and you'll be fair to yourselves while giving the quiz. Okay.
Yes, ma'am.
Okay, so let's start today's lecture then. So last time we studied multisets. Oh, great. Again, it's not showing. I don't know. One of you is from CS, right?
Yes, I am.
Ridhiman.
Yes.
Ridhiman, why it so happens that sometimes even when some window is open, some PDF file is open, Zoom does not detect that window?
We don't study this kind of things in CS.
So as a feedback, I have already told you should figure it out now.
I think you can share the whole screen.
Yes, that's I
You
mean, if
mean
you instead of
desktop?
a window,
There'll
instead
be
of sharing a
one,
window, you can share the entire screen.
yeah.
That's the desktop, right?
Yes, ma'am, there'll be one thing called the desktop, but it will share the whole desktop fully.
Oh, okay, okay. So now is this visible?
Yes.
Okay.
Yes, ma'am.
Yeah. So oh, lecture 9 I should have taken in the continuation. So last time we studied multisets and we saw how we can represent them, etc. Right? Remember?
Yes.
Yes.
and we studied the notion of n multi-choose k and figured it out that it is equal to -1 raised to k minus n choose k. And then the number of sub multisets of a multiset, etc. All those things we studied last time, right?
Yes.
So continuing in the same way, we will today, starting from the representation of a set and how it can be interpreted, we will see some different interpretation for the multiset. Okay, so n choose k, as you know earlier from earlier time itself, means that given n objects, you choose k out of them. Okay, in what order you choose is immaterial. All the objects, so these are n different objects, but n of them. It's not like one object is different from the other. There are n objects. All right. So if this I put, so the set S from which I am choosing the k elements, suppose I choose these k elements in the sense, so as soon as you choose k elements, there are some n minus k elements which remain unchosen. Okay. So I think it got disconnected in between. I don't know if the previous recording also went. Let me share again. Oh, now it shows also. Nice. Is the screen visible?
Yes.
Okay. So I don't know. Till when could you people hear me? So last time we
you
were
are just
seeing how a set can be represented, and how it can be interpreted. Then how the number n choose k can be interpreted. Today we'll see a different interpretation of this number. And from this particular interpretation, we will move slowly to the interpretation for choosing elements for a multiset. Okay. So when we take an element from a set S and we say you are choosing k elements from this set, there are remaining n minus k elements, correct? So you could as well, instead of saying that you choose k elements from n, you could also say that I restrict some particular n minus k elements to remain unchosen. Aren't the two things same?
yes.
And that is why, like a very geometrically, you can see that that is the reason why n choose k is equal to n choose n minus k. Correct? Now, using this idea, what we do is that, so this particular set S from where the elements were to be chosen, we divide the elements of this set S into two categories. First category consists of k elements, which are the elements that you choose. And the second category has remaining n minus k elements. Okay. Now, if you do this instead of into two categories, let's say you have finitely many categories. So you put some AI many elements in category A1 many elements in category 1, A2 many elements in category 2, and so on. So if you're choosing some M categories, you take AM many elements in the category CM. And the condition, of course, is that their summation should be N, because ultimately this is the set which you are sort of partitioning. Okay, so when we did this, you really partitioned your n set into two subsets, one with cardinality k, another one with cardinality n minus k. And now when you want to extend this idea, you want to partition this n set into m disjoint classes such that First class has elements A1, second class has elements A2, and so on. Okay. So these are correspondingly the categories C1, C2, Cn. So just how you knew that this is your binomial coefficient, what you get or write this as n choose A1, A2, Am, this is your multinomial coefficient. And what this really represents, it's the number of ways to place these n distinct objects into m many boxes such that ith box has ai many of these items. Okay. Am I clear?
Yes.
Okay. So this is the multinomial coefficient. Now this again, like if you really say, oh, what happens if I have taken just 2, then this is really n choose some a1 and n minus a1. So in this notation, what we are really doing is that n choose k, you're writing same as n choose k comma n minus k, correct? But
Yes.
since there are just 2 categories, once you have finalized one particular category, the another category is automatically finalized. There is no ambiguity about the second category when there are just 2 categories, correct? Therefore, there should not be any confusion with the notation n choose k or n choose k comma n minus k. They represent the same number. So n choose k is same as n choose k comma n minus k, which is same as n choose n minus k, right? However, when the number of categories is more than 2, you run into the actual multinomial coefficient where the number of categories is more than 2. All right. Now, if you take the set S and you look at its elements and consider their permutation, suppose GS is the set of all its permutations, we will today deal with different operations that would happen on the elements of GS, which means on the permutations of a set S. Okay. Please keep speaking, otherwise it doesn't really feel like a live class.
Okay, ma'am.
Yeah. Okay.
Okay. So, right. So if let's say the set S happens to be the first n natural numbers, you just use Gn instead of Gs, just a shorthand. So this should have actually been G bracket n, but we dropped the bracket and we simply write Gn. Now, how many elements are there in this particular set? The set of permutations of a set S?
N factorial.
N factorial. If the number of elements in that set is n.
N.
Now, so what really is a permutation? You keep on shuffling the elements of the set, right?
Yes.
So permutation is really when the order matters. 1, 2, 3 is different from 2, 3, 1 or 2, 1, 3. They are different. So when you want to, what is the English language? It is nothing but the collection of, or rather, or what are the words? These are nothing but some permutations of the set of alphabets, where alphabets is the set of the English letters which we know, capital A to capital Z, right? So entire English dictionary which you see is nothing but a subset of this G sub alphabets. You see this?
But we don't allow repetition here, right? Or do we?
Yes, and that is the point I was waiting for. So, if let's say we look at the word generating, it has letter E repeating, it has letter G repeating, it has letter N repeating, correct? And as Agilan pointed out, we do not, when we are looking at the permutations of a set, we do not allow repetitions. So, what would happen if we have to allow the repetitions? What should we consider instead of S? We should consider
Multi-set.
a multiset whose ground set is S. Okay, so as you remember, the any word if you say with n letters, it's just a string with n symbols of this form, W1, W2, Wn. So if this is a permutation of a set, then all these Wi's would be distinct. And if not, then some of the Wi's might repeat. Correct? So therefore, to deal with this sort of a thing and making sense of what you have as English dictionary with repetitions, you really consider the multiset M and look at the permutations of that multiset. So if you take the multiset M and GM would denote the permutations of M. So then M supposes the set x1 raised to a1, which means the element x1 appears a1 many times. Similarly, x2 appears a2 many times, and same way xm appears am many times. And the total number is n, which means summation of a1 up to summation of am is n. Is something hitting? You sort of partitioned the entire n into these numbers a1, a2, am. So this happened, and then a1 formed the category C1. So it's like, let's say C1 has the element X1. So you say elements of C1 appears A1 many times. Elements of C2 appears A2 many times. Right? So what really happens with the multiset M with which has these many elements appearing with multiplicity AIs is that the cardinality on the permutation set of this is nothing but this multinomial coefficient. Okay. Do you see the analogy or not?
Yes.
So the n elements have been partitioned into m many boxes, and these m boxes are precisely x1, x2, xm. Okay, each with a cardinality a1. So when you have to find the permutations for this particular set M, which has this structure, the number of elements in this set is exactly this. Okay. As an exercise, you should prove that the multinomial coefficient n choose a1, a2, am is nothing but n factorial divided by a1 factorial, a2 factorial, and so on till am factorial. All right. So this is the exercise will come in your next assignment. You can take a note of it now itself. Now, with this, we have seen the interpretation of multisets. Now we move to different sort of interpretations. So cycle structure, what this is that if you consider a set permutation W, so first of all, W as a set permutation means what? Some particular element goes to some other particular element, right? People who have seen any bit of group theory would understand this very nicely. and even otherwise, I'll make sure that you understand it. So if you have a set S, let's say 1, 2, 3, and another set 2, 3, 4, same set 1, 2, 3, and you take the bijection or other permutation. So what you really say, you are permuting the elements of S, which means you are really changing the location of the elements in which the order in which they appear, correct? So if let's say in the first way you wrote the elements of your set S was A, B, C. Can I try to write here? So if let's say this was the first location, this was the second location, this was the third location, and initially you got elements of the form A, B, and C, then next you write B, A, and C. What have you really done? What has happened is that the location where initially A was, now it has B. Location where initially B was, now it has A. And where it was C, it remains C. So this is a permutation, right? Right?
Yes.
Yes.
And this way, do you have any doubts that a permutation is a bijection?
No.
So any permutation, no matter what S is, if you take a permutation of S, it's going to be a bijection, because that bijection is really coming because of this location, these pointers 1, 2, 3. Okay, it's not because of these things, but because of this. Since every location has to be filled, every location is going to get something. Okay, and since you're doing this thing with a set, once some particular element has been used here, it cannot be used here or here. So therefore, if you say that I have to assign something to this and this and this, you are also saying that exactly one thing gets assigned to this, exactly one thing gets assigned to this, and exactly one thing gets assigned to this. And that's exactly the definition of a bijection. Isn't so?
Yes.
So with that in mind, what we really have is that if you start with some element S, element of S, let's say X, you can talk about WX, right? So if let's say initially if X appeared at the location 2, then WX takes it to location some, let's say R, and then the location at the R goes to some other location, let's say K, and so on. So you consider this particular sequence of X, WX, W square X, and so on. All these are elements of S,
Yes.
right? Because W was a permutation. So it is determined to send the element X to something, and then this was also an element of S. So this also has to go to some other thing. And then this is also an element of S. So on this also you can apply your W and so on. All these elements in this particular sequence are elements of S. And also, since we are like in this course, we are working with finite sets. So S being finite, can I keep on getting new and new elements in the form of X, WX, W square X, and so on?
No.
No. So there would be a point when I would hit one of the previously noted element, right?
Yes.
So if I keep on moving with X, WX, W square X, let's say WKX is the time when I hit one of the previous elements. Can that one of the previous elements be WX?
No, it should be X because the one before WX must be X.
Correct. So what is real, since W is a bijection, we know that if it is hitting something, and that is the first time it is hitting the like it's repeating, first time it's repeating the element, it has to repeat X itself, right? Because if W of K is, let's say, W of X, then WK minus 1 of X should be X, right? Because of the bijectivity of W. Okay.
Yes.
Therefore, given any such permutation, when you consider this as a bijection from the set S to set S, there is a unique. So this is the symbol for unique. It's not not. Okay. So there is a unique L in the set of natural numbers such that WL of X is going to be X itself. So you are taking the first time it hits something from the previous list. Okay, therefore it is the smallest L, and that's why it's a unique L.
Every multiple of L will also work, right?
Correct. But we are interested only in the first time
Small s.
occurrence. And why so is here. So the sequence of X, WX, W square X, and so on up till W of L minus 1X, it's a sequence and all these elements are different from each other then, right? So this particular sequence of L elements of S consists of L different elements of S. And this is called a cycle of W. And the number of elements in this cycle is the length of this cycle. Okay, so the sequence of X, W, X, W square X, and so on till the time it remains distinct. What just happened? Hi, are we connected?
Yes.
Yes.
Okay, so the sequence of X, W, X, W square X, and so on till W L minus 1X. So this is a sequence of L many elements of S all being distinct. Such a sequence is called a cycle of W. Okay, and the length of this cycle is exactly the number of the elements in this cycle. So that is L. All right.
Yes. Okay.
Yes, ma'am.
Now, when we know that W is a bijection, so can it take two elements of S to the same element of S?
No.
No.
No. So if you start with some X, this X, WX, W square X is uniquely determined?
Yes.
So if let's say I call this as a cycle of W corresponding to X, then I now take a different element Y of S and I start looking at Y, WY, W square Y and so on till let's say WK minus 1 of Y. So that is a cycle of W of length K with respect to Y. So can these two cycles be same? X is not equals
Yes.
to Y.
Yes, they
It
can.
can be.
Okay, before that, let me just first say that, okay, so so the cycle X, WX, W square X is considered same as the cycle WX, W square X, and so on till WL minus 1X, comma X, which is then by same logic is considered the same cycle as W square X, W cube X, and so on till WL minus 1X, comma X, comma WX. So all these cyclic rotations of this particular cycle are considered the same cycle of W. Now, can you please tell me if two if one particular element of S can appear in two cycles of W, two different cycles of W. So this particular sequence and all its cyclic rotations are all same, considered same, and are called the cycles of W with respect to X. Now, can X appear in some different cycle of W?
No.
Why?
If it was common, then the term before it and after it must be the same, and so on. So the cycle will become the same.
Exactly. Therefore, if you look at any element of S, it will belong to exactly one cycle. Right?
Yes.
So, with this in mind, oh, I could have moved this part. Okay. So the entire W can be written as product of disjoint distinct cycles. Because once you have considered this particular W and you started with one particular element, you closed up it into this particular bracket, right? Now you take some different element, different from all these L many elements, and you now consider the cycle of W with respect to that element. That is again going to give you a cycle of this type, possibly with some different length. Yeah. Is that right?
Yes.
Following me, Ridhiman?
Yes.
So this way, this entire permutation appears as it could be partitioned into different cycles corresponding to this W, right?
Yes.
And these are the cycles, let's say C1, C2, Ck. So all these cycles are disjoint, as Agilan already told us.
Yes. No element can be common.
No element can be common, because as soon as you get one element common, the entire cycle has to be same for both. Okay, both the cycles have to be same. So these are distinct cycles and these are disjoint cycles. So instead of writing C1 union C2 union Ck sort of thing, we just write it as a concatenation. All right.
Okay.
So if you take this bijection from the 4 set to itself, which sends 1 to 2, 2 to 1, 3 to 3, and 4 to 4. So Ridhiman, if you do not know this notation, this just means that this elements is
Maps
being
to,
sent, right?
yeah.
Right. It maps to this. Okay.
Yes.
So then this would correspond to W being the cycle 1, 2, because 1 goes to 2 and then 2 goes to 1. So if 1 is your X, W of X will be 2. And then W square of X is actually W of 2, which is 1. So you have hit back the X. So 1, 2, 3 goes to 3, 4 goes to 4. So 3 and 4, right? Right?
Yes.
Okay. Now, what if instead of writing 1, 2, 3, 4, what if I ignore this piece initially? Where am I? So let's say I ignore this part and I look at this. 3 goes to 3 and 4 goes to 4, and then later I come to this, because the elements anyway are not ordered, right? So which element should I consider first is up to me. So
Yes.
what if I say you write W as bracket 3, bracket 4, and then bracket 1, 2, or even Y bracket 1, 2? Why not bracket 2, 1? Okay,
Yeah, the same.
they're the same. So 1, 2 is same as 2, 1, but as representation, this and this are different, right? Or for that matter, this and this are different, because here what comes at the first in the first bracket is different from what comes in the first bracket here. So this way representation of W in the disjoint cycles is not a unique representation. And we
Yes.
really want to look for a unique representation, because then the life is easier. When you know that the representation is unique, you do not have to worry about what if it does not determine the W correctly, or what if so and so happens. So to see this, we introduce the notation of digraph. So just how we know what a graph is, Agilan and Saham, have you people seen the notation graph?
Yes, ma'am.
Both of you?
Yes, ma'am.
Okay. So just how, okay, so both of you have seen digraphs also?
No, ma'am. Digraph means directed graph.
Correct, correct. So digraph just means a directed graph. So how in a graph we have vertices and edges, in a digraph we have vertices and edges, but now the edges are directed. So it matters what is the initial point for the edge and what is the final point for the edge. Okay, so that is the only difference between a graph and a digraph. All right.
Okay.
And with this, so in just how in the graphs also, the edge set we know is actually a vertex set of the product of vertex. Edge set is the subset of the product vertex set cross vertex set. All right. So this subset E is a subset of V cross V, where V is the set of vertices. Same way in digraph also, E is a subset of V cross V. In graphs, it's a subset taken without ordering on V cross V. But in digraph, X comma Y would be different from Y comma X. So if you have X comma Y as an edge, E as an edge, X comma Y, then you draw it as with a arrow starting from X going into Y. Okay. If this was a graph, we would have just drawn an edge, no arrow, just an edge. All right. So, okay, these are not any edges of digraph here. Just
And what is the phi?
phi is a map from E to V cross V. So it's actually this sort of inclusion. And what you can see is that if you take, I mean, we won't be using much about the function phi, but what you can see is that if you choose x comma y as x comma x, then you sort of get a loop on x, right? So there is an outgoing edge from x and there is an incoming edge. So, okay, when you have this edge x to y, you say that this edge is outgoing for x because it is outwards from x, and it is incoming for y because it is coming into y. All right. So this is an outgoing edge for x and incoming edge for y, as our intuition tells us, exactly the same way. Now, coming back to this function, so when you have so same so there can be so the set E could have more than, so the set E could take the same element twice as well. Sometimes the set E is actually a multi-set on some subset of V cross V, which means the set, let's say the edge E, which is this x comma y, this itself appears twice in my E. Okay, so this would mean that from x to y, you have edge 1 and edge 2. So there are two edges from x to y. So that's something called a multi-digraph. So some digraph which has multiple edges. All right. However, when this is injective, this will be a simple graph. Okay. Now, so whenever x is not equals y, which means whenever you do not have loops, then D is simple. You do not have loops, and of course you do not have multiple edges. Since I defined it with the sense that E is a subset of V cross V, I do not have to worry about the condition when E could be a multiset. But I have to worry about if x can be equals y or not. So if x is not equal to y, which means there is no loop on any of the vertices of the digraph, then my digraph is called simple. All right. Now, if you take a permutation W in GS, it's a permutation on S, then we construct a digraph corresponding to this particular permutation. How do we construct? We take the, so remember, this really it consists of three elements, V, E, and phi. So for now, just forget about phi. We have to worry about V and E. Okay, so we will have to say what is the set of vertices and what is the set of edges. So if you take the set of vertices to be the set S from which the permutation is coming, all right, and the elements in E are thrown depending on how this W behaves. Okay, remember W was a bijection from S to S?
Yes.
So for every element of S, W sends that element, let's say X to WX. So
Yes.
send X to WX, and so this X comma WX becomes an H in your DW. And this is precisely the set of edges. So you have found your set of vertices, you have found your set of edges. Now can you, okay, maybe before this, yeah. So earlier we saw an example where we said that if you take the bijection W from 4 to 4 to be sending 1 to 2, 2 to 1, 3 to 3, and 4 to 4, then the DW corresponding to this is going to be 1 to 2, right?
Yes.
So this is an edge, 2 to 1, so this is an edge, 3 to 3, and 4 to 4. So this arrow is indicating that this is an edge 3, 3. This arrow indicates the edge 4, 4. This arrow indicates the edge 1, 2, whereas this one indicates 2, 1. Okay, so as you can see, 1, 2 is different from 2, 1 here because we are working with digraphs. All right.
Yes.
Now, so once you have any permutation, regardless of which, whether I wrote it as this or this or this, the digraph DW, which I would construct from this, is it going to be unique?
Yes.
Yes,
Yes. Why?
because the function is the same.
Because the edge set is the same and the vertex set anyways remains same.
Yes.
Each of these elements represents edges, right? If instead of, let's say, a 2 cycle, if I had a 3 cycle here, 1, 2, 5, then I precisely knew the number of the set of edges to be 1, 2, 2, 5, 5, 1. So the edge set and the vertex set is uniquely determined no matter in which form I wrote it. Therefore, given any permutation of a set, its corresponding digraph is unique. All right. So that is the first point. Now, so this was a construction starting from the permutation. Now, if I ask you a other way around question, which is that suppose I give you a digraph, can you determine if this digraph corresponds to the digraph of some permutation? So is this question valid? If so, can it be answered? If so, what is the answer?
I mean, how will you be giving the permutation? Like, as
I
the
will not give
bijection?
you the permutation. I am saying that if I give you a digraph,
Okay.
can you tell me whether this digraph comes from, or if this is isomorphic to digraph of some permutation?
Are we assuming that this vertex set is finite of the digraph you have given?
Yeah, assume
So,
that the vertex set and edge set both are finite. And that S is not a multiset. Clearly, if S becomes a multiset, then clearly it can't be achieved as a digraph corresponding to some permutation, right? Because these permutations are on a set. So every element.
hello.
Yeah.
I think for the 5th time in a row, it got disconnected. I don't know. Okay, so clearly if the edge set happens to be a multiset of the digraph which I gave you, then this cannot correspond to a digraph coming from a permutation because every element here appears exactly once. And so is the case on this side, right? That's why it's a bijection, correct?
Yes, ma'am. I was saying that for the digraph to be a valid permutation, doesn't the number of edges and number of vertices need to be equal? Because for each element we are mapping it to only one other element. So there are n mappings only.
Wasn't the characterization Agilan gave sufficient and necessary as well?
Yeah.
Oh, I only heard what Riddhiman said. Agilan, you said something?
No, I told that like the in degree and out degree should be 1 for each vertex, and it should be exactly 1, not more than that, less than that.
That's correct. Why? Because when you look at any cycle here, it has exactly one sort of left neighbor and exactly one right neighbor, right?
Yes, right.
And that's precisely the condition which characterizes the digraphs which correspond to digraphs coming from some permutation. Coming to what Riddhiman said, that the number of edges and the number of vertices should be same, I can rule that out very easily by doing that. If you take the digraph and here instead of taking 1 2 and 2 3 1 2 and back to 2 1, I could have taken 1 2 and 1 2.
I mean, how
Or
would that give a permutation?
Or for that matter, I would drop the edge 3, 3 and I would add an edge 2 to 3. Then you will have the vertex set with 4 elements. You will have 4 edges, 1, 2, 2, 1, 2, 3 and 4, 4.
Yeah,
But
what Ridhiman is saying is not like sufficient, but it
Okay,
is necessary. Yeah.
it is
yes,
not
exactly.
necessary either. I just showed, no? Yeah, it's necessary. Right, right. I'm so sorry. It is necessary. That much is at least needed.
Yes.
If the number of vertices falls short of the number of edges or the other way around, then certainly it cannot be corresponding to some DW. However, there are examples as we constructed. You could have taken this as an edge and just forget about this edge. Okay, so then the number of edges is 1, 2, 3, and 4. However, this particular digraph will not correspond to any digraph coming from a
Permutation.
permutation. Okay,
Yes.
so drawing a digraph corresponding to a permutation gives a unique way of representing a permutation. It's definitely a geometric representation. But as we were worried up till this point that given a permutation, there was no unique way of writing a permutation or representing a permutation. We have one representation via in the form of digraph where it is unique. Now, if we say, oh, we don't really want to go into digraphs because then this is a very off topic. Well, in such a case, let's grill our minds more and we see how this W can be written in some sort of a standard way, which will remain unique. Okay. So that is called the standard representation of W. In this, what we do is that there are two rules. First rule says that each cycle is written with largest element first. So if let's say it has these three cycles are there, right? So in all these cycles, remember we said that cycle 1, 2 is going to be same as the cycle 2, 1. This particular line that x wx up to wl minus 1 is same as cycle wx w square x wl minus 1 x, which is same as the cycle w square x and wl minus 1 x wx, and so on, right? So that is why from this cycle when the working underlying set of elements is the square bracket n, you can have the largest element possible for each cycle. Okay, write that particular element first and the following ones coming as per this order later. So each cycle can be written in this format uniquely, right?
Yes.
So if I tell you the cycle 254, tell me as per rule 1 what I should write it. 254.
542.
So this becomes 542. If I had this as my cycle,
8254.
8254. You just have to pick the largest element and then later elements come as a trail, right? So this was rule number 1. Now, once you have applied rule number 1, you know that each of the cycles are arranged in a certain fashion. And in that fashion, the largest element appears first. But there are more than one cycles, most probably. If there is just one cycle, there is nothing to worry about. Already the representation is unique. But the problem majorly was because there were more than one cycle. Isn't that so?
Yes.
So what really should be my condition on arranging these cycles is that you put the cycles with the smallest number in the first place, and that cycle comes first. So cycles are written in increasing order of their largest element. So if this was the cycle, so I already arranged and wrote it as 2, 1, 3, 4. Now, what is the largest element in this? What is the first element of this cycle?
2,
What is the first element of this cycle?
3,
What is the first element of this cycle?
4.
So you collect these first elements of these cycles, okay? Pick out the smallest of those. And now this smallest corresponds to some particular cycle here. Write that cycle first. After that, removes from this list also. Okay, so from this, I have a 2, I have a 3, and I have a 4. Okay, so this 2 here corresponds to this 2, this cycle 2, 1, right? So I would write my 2, 1 first and get rid of this 2, 1 and get rid of this 2. Now, what is the next smallest element amongst this list? It is this 3. So now 3 corresponds to this particular cycle here. So then I'm going to write the cycle 3 and get rid of this 3 here, get rid of this 3 here. What is the next smallest element here? 4. 4 corresponds to here. So actually the 2, 1, 3 and 4. This is a standard representation of W. Understood?
Yes.
Let's see. So with 2, 1, 3, 4, this was we just saw. If let's say we take W to be 1, 2, 3, 4, 5, 6, 7, 8, 9. So as per the first rule, I should rewrite these cycles within. So first cycle becomes
4, 1, 2, 3.
Oops. 4, 1, 2, 3. Then
6, 5,
6, 5. Then
7, 9, 8.
okay. Now collect the smallest element, the first element of this cycle. What is the smallest element of this cycle? Here. Sorry, largest element of this cycle, which is the first element, right? So this is this. Then here, this is this. So first element, I'm just going to blindly collect and put these elements into a set now. So 4, 6, 7, 9. So I get this new set now, 4, 6, 7, 9. This is a 6. All right, what is the smallest among this? 4. So this is the cycle which should appear first in my standard representation. Then follows by 6. So this is the next cycle, then this, and then this. Okay. So the standard representation becomes 4, 1, 2, 3, 6, 5, 7, 9, 8. Okay. Now, once you have formed the standard representation, I introduce another notation, say W hat. What you do from the standard representation, you just drop the brackets and write these numbers in a sequence. So 4, 1, 2, 3, 6, 5, 7, 9, 8. So for this particular standard representation 2, 1, 3, 4, it was 2, 1, 3, 4 without the brackets. Okay. 4, 1, 2, 3, 65798 as we obtained here becomes just the huge sequence 4 1 2 3 6 5 7 9 8. Wow, what we ask next is that, can you really recover W from your W hat? If I tell you that this is my W hat, can you come back to this? Because you see
Yes,
now,
because the biggest elements appear at the beginning of a bracket. So if we, we start looking and we consider everything in the same cycle until we hit a number which is bigger than the number we started with. And in that case, we go to the second cycle.
correct. So what Ridhiman is saying is that since we wrote the cycles in such a way that the largest number appeared first for each cycle, and then these cycles were arranged such that the largest number of these cycles were put in the increasing order, which means if I start with 4, then everything which follows 4 and is less than 4 is part of the cycle corresponding to the 4. Okay. So after the 4, I have 1. 1 is less than 4, which means 1 would have been part of the cycle of 4. 2, of course, would belong to the cycle for 4. 3 will belong to the cycle for 4. And then I hit a 6. 6 is bigger than 4, which means here the cycle would have changed. Right? This was the rule 2. Cycles are written in increasing order of their largest element. So here the bracket opens, but as soon as you see something which is bigger than this number, you close this bracket and open a new one. Now, when you hit 6, you know that whatever appeared earlier has to be smaller than 6 anyway, because 6 was larger than the largest element of this cycle. Correct? Agilan?
Yes, ma'am.
Following me?
Yes, ma'am. Yeah.
Saham?
Yes, ma'am.
Okay. And then you keep moving till you see elements smaller than this particular number. So 5 is smaller than this, 7. 7 is not smaller, which means 5 belongs to the cycle of 6, but 7 doesn't. So you close the bracket you opened for 6 and then open a new bracket. And now 7. Now everything on the left of 7 has to be smaller than 7 for the same reason that 7 was larger than the largest elements of these cycles. Okay, so you keep moving right again and see until you hit a number which is bigger than 7. You hit a 9, it's larger than 7. So you open the bracket for 7, you close the bracket for 7, and then for 9 you do the same thing. So you have really recovered back from W hat your W, right? So that's what I've written here. So forget about these. So you open a bracket here. Once you see a number larger than 4, you open another bracket. You see a number larger than 6, you open another bracket. You see a number larger than 7, you open another bracket. And then just before these, you put the closing brackets, which means the operation W to W hat is a bijective process, where W here is considered in the standard representation, right? Not any representation would yield this. All this business of opening bracket and closing bracket at the correct positions could happen because we had arranged the cycles of W in a certain fashion, right? Therefore, if W happens to be in the standard representation, then W hat is a bijection. And this leads to another topic of interest, which is called the indicator of a cycle or an index of a cycle. So once you have this notation W, and you saw that any W when you write appears as product of disjoint cycles, and each cycle has a certain length. What is the smallest length of a cycle?
1.
1. What can be the largest length of a cycle?
N.
N. So if, let's say, I say you collect first the cycles of length 1, then the cycles of length 2, and then the cycles of length 3, and so on, and I record this information into a sequence of n numbers where ith location really denotes the cycles of length I. Okay. So don't worry about this. We have to first understand from here, you see. So in W, brackets are put so that first Ci cycles have length 1. Next, sorry, this should be C1. Next C2 cycles have length 2, and so on. Okay, so this is going to give me a n vector. So for any W in Gn, you have the n length vector C1, C2, Cn, such that C1 is the number of cycles which have length 1, then C2 is the number of cycles having length 2, and so on. So now if you write any W and you give me any sequence, this together determines a permutation. So when I say C1 is 1 and W is just a number 4, 2, 1, 5, 3, it tells me that there is one cycle of length 1. There is one cycle of length 1, right? Which means for 4, I have to put a bracket. Then it says there are 2 cycles of length 2, which means what I hit now is a 2 cycle, and then after that there is another 2 cycle. Okay. So after the 4 has been taken care of, I see 2 numbers and put a bracket, and the next 2 numbers again I put a bracket because my C2 is 2, which means there are 2 cycles of length 2. Hello?
Hello.
Yeah, I don't know. See, when the meeting ends, I don't know if the entire recording will be generated or not because it has disconnected so many times. I don't know.
I
Let's,
think the recording will continue. Like you'll get one file.
I hope so. Otherwise, I'll have to shift the data. I mean, even if it makes 4 or 5 recordings, I'm fine. I can put part 1, part 2, part 3. But I mean, this is the reason why I could not upload, I think, lecture 2 or something, because it kept dropping, and then because of that the full recording was not there. Okay, so as we were saying, so since C1 is the number of cycles of length 1 and there is only one cycle of length 1, so 4 was bracketed. There are 2 cycles of length 2, so these 2 brackets have come. Therefore, so this particular vector is called the type of a permutation, because this, when given with a valid number here, uniquely determines a permutation. This is called the type of W. Now, when you write t raised to type of W, t is a variable. In some sense, you should try to understand this as a multivariable. So this really means that, so t has n parts. Type W is already a n vector. So it's a t1, t2, tn raised to c1, c2, cn. So it expands as t1 raised to c1, t2 raised to c2, and so on, product tn raised to cn. Okay.
Ma'am,
Huh?
Yeah, here, like, are we defining type for, that is, we already have a permutation and then we are defining the type for it, right? Or
No, 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 no. So when you say the type of W, W is just a number. Okay, you see, it's just a number. And then along with that number, when you give me a type of W, that type of W along with that number determines the permutation W.
but there are some restrictions on the type, right? Like,
There aren't.
for
So
example,
for that matter,
Okay.
this 1200, and if I like change the W here, it will determine a different W here as a permutation. So this W doesn't have to be in a standard representation or anything, nothing of that sort. This is in general that given a number, a valid number, by that what it really means that this product and sum has to really match up the number of elements in this word. As a word, you are just seeing this. So there are 2 cycles of length 2, which means 2 into 2, 4 elements, and there is 1 cycle of length 1. So there is 1 into 1. So 1 plus 2 into 2, which is 4. So 1 plus 4 is 5, and then rest is 0, at least in this case, which means there have to be 5 elements in the string. That's all that makes it into a valid string. If this was, let's say, a different thing and I had, let's say, a 1, 0, 2, this is 0, okay. I had only just this much, let's say, as my C1, C2. Oh, there should have been a C5, I'm sorry. This should have been a 5 vector. It's a typo, please correct this. This was a C5 also here. And it will have value 0. Okay, so if this happened to be the case, let me not close the bracket here. What it really says that this will correspond to 1 element, and then you have 0 element, and then you have 2 cycles of length 3, so 6. So which means your W, length of W is going to be 7. So now you tell me any digit with 7 different digits, or rather 7 different letters, it will remain valid, and from that data I can generate a permutation. Okay, am I clear, Agilan?
yes, ma'am. But here also there must be 4 more zeros at the end, right?
Yeah. That's what I said. Let me not close this bracket. Depending on what I figure out to be this number, this actually is going to be a 7 string. That's right.
Okay, yes.
I naively wrote it and closed it, and then as soon as I realized this, I said that it doesn't close here.
Okay,
So
ma'am.
this is going to be a 7 string. Okay.
Yes.
So so once you understand what is type of W, this entire theory relates nicely with the generating functions also. And before that, let's just define the cycle indicator of Gn, or the cycle index, to be the number Zn, which is a variable in the, I mean, it's a polynomial in n variables, t1, t2, tn, which is defined as 1 upon n factorial summation t raised to type of W, where W runs over the entire permutation set. Okay.
Okay.
So
Ma'am,
there,
can you go down a bit, the previous,
you're done.
below, ma'am? So you're starting with a W without brackets, is it?
Right.
So like type of W means this type depends on W, right?
Okay, so let me put this out in another way, that if this is given to you,
Yeah, then we can write the type.
then you can write the type.
Correct.
If type is given to you and a W is given without any extra information, then you can generate your W back. So in that sense, type W determines the W, given either this or this. If this is given to you, it uniquely determines this type.
Okay.
If this type is given to you and a W is given without brackets, it uniquely determines this W.
So in that summation,
Yeah.
are we given with W's with brackets or without brackets?
These W's are given with brackets because they are coming from GN.
Okay, yes.
But this type of W can be widely seen through this information.
Yes, ma'am. Yeah.
Okay.
Yes, ma'am.
So just concerning this material, there are a few results in the book. You should look it up. These are small propositions. And the main theorem which says is that the summation Zn x raised to n. So you already see that this is a generating function, right? With coefficient Zn.
Yes, ma'am.
So something with coefficient Zn, generating function, gives this as the polynomial. So this turns out to be the function. E raised to t1x plus t2x squared by 2 plus t3x cubed by 3 and so on, where Zn was given by 1 upon n factorial summation t raised to type of W. Okay. Now to see a quick application of this particular theorem, let's say E6n be the number of permutations W in Gn which satisfies W raised to x equals to 1. Okay, which means cycle, like the, what is it called? The order of this element W is 1. Which means if you repeat this 6 times, you're going to get back the, in some sense, as if no
Identity.
permutation happened. Everyone understands this notation? W raised to 6 is 1.
Yes.
Especially
Yes.
Ridhiman.
Yes.
So if W was a permutation 1, 2, 3, then will W6 be 1?
Yeah.
Yeah. Will W4 be 1?
No.
No. It needs
What
to
will
be a multiple
W4
of
be?
3.
It will be W1.
Correct. So you have figured out already that W3 is 1. And W raised to 3 is the smallest, 3 is the smallest number such that W raised to 3 is 1. Right?
Yes.
But here we are saying satisfying W raised to 6 is 1, which means something which satisfied W raised to 3 equals 1 also satisfies W raised to 6 equals 1.
Yes.
Also, if W raised to 2 was 1, W raised to 6 is 1.
Yes.
Also, if W itself was 1, W raised to 6 was 1.
Yes.
Right? So, W raised to 6 is 1 if and only if all of cycles will have length that would divide 6. That is really what you are doing in your head also.
Yes.
Right? And what are these numbers? 1, 2, 3, or 6. So to count the number of these permutations, we have to really figure out this Zn for the specific values. Okay. And then in between you would have to find the whatever mixing happens. And here the which all should, okay, so let me, so here this Zn involved n many variables. Should all n variables appear? Or only the ones which can contribute to this number should appear? Remember what were these TIs? TIs were, oops, sorry, here. So TIs were coming from the type. So if C1 is raising to the power of T1, C1 was the number of cycles of length 1. Okay. So when I'm looking at those cycles that divide, I mean, whose length divides 6, should I here consider something, some cycle of length 5?
No.
No. So what that really tells me is that for such W, for such a qualifying W, the C5 is going to be 0 for any such W.
Yes.
C4 is also going to be 0. Correct?
Yes.
So for this polynomial, when I am raising these powers, so here I can just, I mean, something which will raise to this power, that will anyway become, if I raise to a power 0, that variable will vanish.
Yes.
So using this theorem and this data, you put Ti to be 1 only when I is dividing 6, and otherwise you keep it 0. Because you are working in exponential, right? So what survives? T1, which was the coefficient variable here. T2, which was the variable here. You compare it with this here. T2 survives. T3 survives. T4 doesn't survive. T5 doesn't survive. T6 survives. And T7, T8, nothing else survives. Right? And this happened to be exactly like this because E6n, it already was n factorial Zn. So n factorial, when you multiply here, I mean, okay. So Zn x raised to n is exactly this number. And therefore, you get that this, the generating function for this E6n is this. Now question, or rather last point to see today is that, can this entire information which we saw for W6 equals 1, can this be generalized to the cases of permutations when WR is equal to 1 instead of 6? So here what we did was R equals 6. Can this be done for any arbitrary R?
Yes.
Yes, and method is exactly the same. Okay. So this was all about cycles. There is, I mean, there are few more examples worked out. You can see them. And then there is a sort of reverse kind of technique to understand these interpretations called inversions. So that's a very small topic. Read that up, and next we'll see descents. Okay.
Okay.
So yeah, please write back to me at least like 5-6 hours prior if you need more time for the assignment. And rest everything we have already discussed. I will see after the meeting ends, then only I'll be able to figure out if the recording happened for the entire lecture or not. Nevertheless, these notes I'll put up on the Moodle. Okay.
Okay.
Okay, see you. Bye-bye.